This video will talk about variables, controls, and graphing for a science fair project, which could also include an engineering project because we do have to test, which would require variables and controls, and graph our results even for our engineering projects. So let's take a look at this chart. And I want to talk to you a little bit about what an independent variable is and a dependent variable. So as middle school students, you actually have worked with independent and dependent variables anytime you've had to graph any sort of data. And so I want to take a look at this particular chart. I think it's fairly simple to read. We're looking at the date in this column, and it's being placed along our x-axis. And so I'm just going to remind you that this is our x-axis. Okay, and so this column, when you have a chart, the first column is always your x-axis. And then we have the numbers that are coming out. And so we're plotting up our y-axis over here. This guy's going to be our y-axis. And so look at the numbers we're plotting. We have a point on a 20, a point just above a 40, another point just above a 40, something in the 50s, maybe something in the 90s. These are coming from this particular column. And so if you look, sometimes there's extra data, and this column would be considered extra data, which is not on our chart. Nowhere on our graph does it say east, west, whatever. So we can kind of like say, hey, he doesn't matter for this particular thing that the graph is trying to show you. And so what is it that it is trying to show you? It's trying to show you that on May 1st, 20 houses were sold. On May 2nd, 42 houses were sold. And that's what these particular dots are representing. And so this next column, anytime you have a chart, the first column is always going to be your x-axis, and the second is always going to be your y-axis. So thinking that this is our x-axis, and this one is our y-axis, okay? Then what we can say is look at how this information came to be. So the first thing, in order to be able to graph this, was that you had to look at May 1st and figure out how many houses were sold. And the number of houses that were sold turned out to be 20. And likewise, when you want to graph the next point, you have to look at how many were sold on May 2nd in order to allow it to connect to the 42 houses that were sold. So our x-axis is often called our independent variable, or the information that goes on our x-axis is called the independent variable because the number of houses sold depends on this particular date in this case. And so in order to get a number to plot on our graph, which is our number sold, we have to look to a specific date to pull that data. Therefore, our independent variable, which is shown along our x-axis, is often called the input. When I look at the date, what is the number of houses sold? And so that means I get an output. Okay, the answer for my problem is dependent on what I plug in. And so when I plug in a date in this particular case, I get out the number of houses sold. So I want to take a minute and I want to remind you that when you're doing graphing and you display this graph, you actually need your x-axis title. Well, we've talked about it being about the date. The date was specifically what was inputted, like May 1st, in order to get out the number of houses, which is 20. So we're looking at date being our x-axis, but we would actually call that time. And we would always write in capital letters, and we would say that we measured time in days. And if you look, we did May 1st, May 2nd, May 3rd, May 4th. Those are all just one day at a time. So we're counting by days. This could have been years. It could have been months. It could have been weeks. But in this particular case, we were looking at days. So our x-axis is time. I wrote it all in caps. And then days is how I measured. Now my y-axis is actually the number of houses sold. So over here, I would write houses sold. And how did I count them? I just simply counted them by numbers. 20 does not mean 20,000. It means 20. If I wanted it to mean 20,000, I could put number in thousands inside my parenthesis. And that's how I would represent 20 as 20,000. So if I want to take a look at this graph and I want to understand what it's saying to me, I can look at my numbers and they are starting at 0 and they are moving to 50 along my x-axis. My x-axis has a title of temperature and they've measured it in degrees Celsius. I would have recommended a dot with the C, but that's okay. Then if you look along your y-axis, you're moving from 0 to 90 and it's measuring light intensity and it has a unit of measurement in the parentheses. So how do we make statements about this? This is where our results and our conclusions come in. We say, oh, as the temperature increased towards about 30 degrees Celsius, the light intensity increased to a height of about 80. And then from 30 to 40 degrees Celsius, the light intensity decreased. So we have two trends here. We have this kind of upward increasing trend. As temperature increases, light intensity increases. But then we have another component we have to pay attention to. And it falls between that range of kind of 30 and 40 degrees Celsius, where the light intensity was decreasing. And you would want to mention both of those things. So if I was looking at how this graph was made, it was made from a data chart. And we know that our x-axis is always the first column and our y-axis is always the second column because we input something and we get out an answer. So in this case, we're going to input 10 degrees. We're going to input 20 degrees. We're going to input 30 degrees. And we're going to figure out what happened, what came out. So our x-axis is actually temperature, and it was in degrees Celsius. And our output is our light intensity, and it's measured in the candleless. So we have the point at 0 degrees Celsius, we have about 11 candleless of light intensity. At 10 degrees Celsius, we have an intensity of maybe 18. At 20, we have an intensity of 35. At 30, somewhere up here, we have about 78. And we might want to mention a 35. At 35, we have about 60. And at 40, we have somewhere around maybe 21, 22. So this is what the data chart may have looked like that made this particular graph. And so once you realize how these two things work together, then you can utilize programs like Sheets and Excel in order to create your data charts in Sheets, and the computer will create the map or the graph for you. You just have to understand how to put it in the right order. And so remembering that your x-axis is always your first column, and your y-axis is always your second column, you have a better chance at getting the computer to show what you want. So this data chart is probably a little bit closer to what yours might look like from your science fair project. And so that's because you're not just going to have a single x value and a single y value. And so we want to look at what this chart is trying to tell us, and we want to look at being able to create this as a graph for ourselves. So this is saying that when I have one mouse, in week 1, I had 6 grains that were eaten. In week 2, 8 grains that were eaten. In week 3, 14 grains. Or sorry, not grains, grams. For mouse number 2, it ate 5 grams 1 week, 4 grams the next, 9 grams the third week, and so on. So this is looking at a whole lot of different information only because this chart does not have a good control. They fed the mice different food. And so what are we comparing? Are we comparing and looking at how mice eat over a period of 3 weeks? So if our question is something like, so this particular data chart, we could look at 2 potential questions that we were answering. The question could have been, how do the eating habits of mice change as they grow? And so mouse number 1 is growing and getting larger, and these are the things that he ate. And we would use the number 1 and this particular column as our x-axis in this case. However, if we are looking at how does the type of food affect each mouse and how much they eat, then this is going to be our x-axis, and we're comparing how much they're eating based on the food that they're eating. So we need to decide what information is important. What am I trying to show? So I have all of this wonderful, fabulous data in this chart, but I need to create a graph that actually answers the specific question that I want to deal with. So let's look at what we might do with that and how it would look. So I'm going to start with this first question. How does the eating habits change as they grow? So I might say that I'm looking at the age of the mice, right? And how much food they are eating each week. So age, or how old they are, is going to be my x-axis. And that really is talking about time. You could name it age. You just want to make sure that you're recognizing that we are measuring this age or this amount of time in weeks. So either of these would be appropriate as long as you acknowledge these are weekly measurements. So you have week 1, you have week 2, and you have week 3. And now that made this particular age the x-axis, which isn't actually showing on this graph. We have mouse number 1, mouse number 2, mouse number 3, mouse number 4, and then we have these weeks of measurements. Well, how much they ate is going to pop up over here. So we know we're measuring in grams, and this is like the amount of food would be our y-axis. And so we're going to look at week 1, our first mouse. Whoops, that was too bright. Let's erase that. So our first mouse ate, we need some lines up here. So 1, 2, 3, 4, 5, 6. Ate 6 grams. And then at 2 weeks, it ate 8 grams. And then at 3 weeks, it's way up here at 14. Well, then we really need to look at our second mouse, our second piece of information. And it's going to go on the same graph. This is almost like the second time you performed this experiment. So like test 2. Test 2 says he ate 5, and then 4, and then 9. And now this one would be test 3. So at 1 week old, it ate 8, and then 4, and then 12. And now we're down to our 4th experiment. And at week 1, it ate 12, and then it ate 8, and then it ate, I think that's a 20 under there, so something way up tall. Now all of these numbers do not have to be different colors. I'm trying to show you that they were test 1, test 2, test 3. The reality is that they should all really be the same color. So the reality is that we should put all of our different tests, and in this case it was 4 different mice, so 4 different tests, in one color. And just make sure that we are labeling correctly our X and our Y axis. And then if you can, and there is a trend, which I'm not sure this data shows a trend, but you could, instead of connecting dots, you say, hey, there is kind of this upward trend. Now again, this data kind of does this, and then it does this. I'm not actually sure it shows a trend, but if it does, a best fit line through your data in another color would show your trend. And then you can make statements like, as age increases, the amount of food increases. But we had another question that we could test. So our other question looked at how does the type of food, making this particular column our x-axis, and each of these values that we would want to chart on our graph. So what might that look like? So we have a little bit different situation. So we want to have an x and a y axis, but we're looking at type of food down here. Well, what types are we looking at? We can't call it 1, 2, 3, 4 and show change. So this really is rice and grain and corn and some sort of a mixture. And we're looking at how much they ate. Well, when we want to look at how much they ate, we then might want to look at over week 1 compared to week 2 compared to week 3. But you would want to make sure that you acknowledged all of them. So to do that, you would say, okay, well, how much was rice? And I'm going to make rice blue. And so rice on week 1 was 6, and then it went to 8, and then it went to 14. Well, we might actually want to add and get a total. So 14 plus 6 is 20, plus 8 is 28. So we might have this bar that jumps up all the way to the number 28. And then we would have, for grain, add them all together. 9 plus 9 is 18. So grain, I might do, well, I probably leave it as blue too and just put it up there. And this one went to 18. And now when I look at corn, I can add 12 plus 8 and get 20, plus 4 is 24. So I end up somewhere around here. And my mixture was 20 plus 20, which is 40. And it would be super tall. And this would be 40. And now I have a bar graph situation. So what I want to make sure that I remember is that this is how much they've eaten over 3 weeks. And it's measured in grams. So this is 28 grams, 18 grams, 24 grams, 40 grams. Different situation, definitely gives us a bar graph. I would make note right now that your big takeaway should be this, that we really believe that when you're doing a great grade level science fair project, that your graph should come out as a scatter plot, that your x-axis should have some sort of numbers or quantity so that you can show change over time. So think about converting your question from something that looks at how does each food type or looks at a brand and instead looks at the effect when you test it multiple times like we did with our mouse. And so if we get rid of this column and it's not about the type of food, then we end up with a number along our bottom and we end up with a scatter plot situation like you saw the first graph that we made. So just a refresher, your independent variable is going to end up being your x-axis, and you really want it to be a number or a quantity. This is also called your input. As I change this value, I'm going to get out something else, and that something that you get out is your dependent variable, which gets charted on your y-axis. It should also be some sort of a number, and we call it your output. As I plug something in, as I make a change to the type of food my mouse eats, I'm going to get out a different answer of how much they eat. As I look at mouse 1 versus mouse 2 versus mouse 3, I'm going to get out some different output values that can then be graphed. Now, what we want to do is we want to provide an experiment that's well controlled. So we're going to take a look at what it means to be an uncontrolled variable versus a controlled variable. So controlled variables are those things that we have really tried to look at in our experiment that is going to make our data very precise and not have any sort of issues. So if I'm thinking about the temperature, and we had if I'm thinking about, the temperature, and I want to record the temperature over 10 days, what things could I control in that project? Well, I could do my test at the same time, at the same exact time of day. And now I'm not comparing morning to afternoons. I'm controlling the time that I get that temperature out. So I want to try to do my project at the same exact time every day. If I'm growing plants, then I would want to water my project at the same exact time every day. So if I'm thinking about this plant and I need to watch him grow because I'm feeding him some different fertilizers or different things into his soil, maybe it's different water, different minerals, whatever it is, there's lots of things I can control. One of them, we said, was the time of day. But we want to control the amount of water or food that is being fed. We want to control the temperature of that water or food that is being fed. When we plant this plant in his little container, I want to make sure that I have the same size containers. I want to make sure that I started them all from seeds. I want to make sure I use the same amount of soil, that they get the same amount of sun. I want to do everything I possibly can do that if I have more plants in bins, that they are all getting the same exact opportunities other than the variable that you are trying to change. So if you are trying to change something like, say, the fertilizer, then they might have the same soil, but the uncontrolled variable is the amount of fertilizer. And so this one might get 1 ounce of fertilizer every day, and this one might get 2 ounces of fertilizer every day, and this one might get 3 ounces of fertilizer every day. And so that is the thing that you are changing to figure out how tall this plant will grow in a certain amount of time. If I'm looking at types of fertilizers, then maybe this plant would get fertilizer A, and this one gets fertilizer B, and this one gets fertilizer C. The problem is the types of fertilizer are going to result in a bar graph, which we really would not want. Whereas the amount of fertilizer is going to say, when I have 1 ounce of fertilizer and 2 ounces, and 3 ounces of fertilizer, I'm going to get some growth from my different plants, and I'm going to end up with a scatter plot rather than the bar graph. So variables can be controlled by simply taking a minute to think about all the things that you can make the same. And if you can control your environment and you can control your amounts and your temperatures, then you've done a good job controlling your experiment. And you want to try to take all the human error out of the project and leave only your dependent variable as your uncontrolled variable. So let's look at this sample project. A group of middle school students were given a short course in speed reading. The instructor was curious if a monetary incentive would influence performance on a reading test taken at the end of the course. Half the students were offered $5 for obtaining a certain level of performance on the test, and the other half were not offered any money. Okay, so if we're looking at what's changing, we're looking at whether they had money or not. That's what we're looking at. That's what our x-axis is. A group was given money, a group was not given money. And then what were we getting out of this? We're getting out their performance, which means some sort of a grade on a test. So this is the grade on the test is the outcome. So we would compare the people that were getting money or not getting money based on their grades. So if I had to make a chart, this would be grade and probably in a percent. And our x-axis would be, this group would be the got money and this would be no money. And so maybe we would call it students because that's what we're looking at is students that got money or didn't get money. And then there's a certain number that got, here's all the different grades on the test from the different students that took it. And here's, maybe we're saying they didn't get good scores because they didn't get any money. And if this were the case, we could say money influenced test scores. We could also graph this as a pie chart, especially with people. So if it were a pie chart, it might be, whoops, that was a terrible pie chart. If this was quarters, maybe it's this many people, and black is the people that got the money. And this group is the people with no money. And so then you can clearly see the people with money got the better scores. Okay, that's fine for how this might graph. Definitely gave us a chance to identify our independent and dependent variable. But what about controls? What controls could we put onto this project? What are our controlled variables? What are our uncontrolled variables? So if I had to make a list, I could list what things I could control. So the amount of time students had to take the test could be controlled. Everyone is given the same test. You could also make sure that everyone received the same instruction. You could make sure that everyone was the same age and had the same teacher. You could make sure that everyone had a snack before the test so they weren't hungry. You could make sure everyone that had a sharp pencil. And you could control all of these things to say, hey, I'm trying to give everybody an equal chance. So what things can't you control? You can't control a person's IQ. You can't control how they're feeling. Maybe they're sick. Maybe they didn't sleep well. So you don't know how well they slept, how long they slept. You don't know if they got in a fight with their mom or dad. You don't know if they got a car accident on the way to school. So all of these things are kind of the human element, and there's a lot that when dealing with a human project, you cannot actually control. You can't control that people will do their best just because you ask them to. So lots of uncontrolled elements in this particular project because it deals with humans. But there is a whole lot of components that as an experimenter, you can try to control to give your project the best element and able to collect the best data, the most precise data. So here's another example. It's January. Haley, Sarah, and Becky are tired of having cold feet while waiting for the school bus. So they decide to design an experiment to test the effectiveness of wool, cotton, and nylon as insulators. They fill identical bottles with 20 milliliters of water at 100 degrees Celsius, and they place them inside each sock. They take the temperature of the water after 20 minutes. So if we're looking for independent variables and dependent variables, what are they getting out? What are they recording? What are they collecting and going to chart? They're going to chart the temperature. So their dependent variable is temperature. Temperature. Okay, well, and they're collecting that temperature, it says, after 20 minutes. Okay, so they're going to let the water sit. What are we looking at? We're looking at comparing wool, cotton, and nylon. Okay, so again, these are not numbers. So these guys are going to end up giving me a graph that is not a scatter plot. It's going to end up giving me some sort of bar graph, okay, with the wool, nylon, and cotton being the x-axis. And that's okay. And our amount of temperature at the end of 20 minutes is how high these little bars are going to be. Okay, so those are our independent and dependent variables. What about the controls that we could put on this project? So they give us some good information. They tell us that they're doing identical bottles. So that means that they controlled the bottle size, shape. That's all controlled. They're using 200 milliliters of water. So the amount of water has been controlled. They also tell us that they're going to start the water at 100 degrees Celsius. So that means the temperature of the water has been controlled. Okay? And they're going to record the amount after 20 minutes. So the length of time that they're performing this experiment has been controlled. They are then placing these water bottles into socks, and they're going to record at the end of 20 minutes the temperature of the water. So the uncontrolled variable right now is the sock type, which is good because that's the thing that we're comparing, and we want it to be the only uncontrolled variable. Well, what other things come into play? The temperature outside, the temperature where you put these bottles. However, if you place them all in the same place, whether it's outside on the step or inside on the counter, then you have controlled the temperature. You have controlled the environment. You have made sure that everything else stays controlled, leaving only the sock type as your uncontrolled, which is excellent. So what I might ask is, how do you turn this into a scatter plot graph instead of a bar graph? So if I want this to be more of a scatter plot graph than a bar graph that shows a winner, I might want to take the temperature more often than just after 20 minutes. So I might actually make this my time and measure it in minutes. But what that does is it says, hey, at 1 minute, what is the temperature in the nylon? What is the temperature in the wool? What is the temperature in the sock? So we know that they all start at 100. So at 0, the nylon or the wool, let's make wool blue, is at 100. And cotton, which is going to be red, is also at 100. And nylon also started at 100. And now after 1 minute, you can check their temperature. And maybe you want to wait, and after 5 minutes, you want to check their temperature. And so maybe then you can show that one drops faster than the others. And you want to record again after 10 minutes. And then you want to look at 20 minutes. And you want to see which one holds the temperature over time the best. So you really are looking at the same project, but we're looking at change in time. And because we're looking at change over time of minutes, we actually can have a scatter plot, and we can actually see that the project can take different temperature measurements at different time periods than just the 20 minutes, creating a change over time. So just to recap, we've covered variables and the fact that you have controlled and uncontrolled variables. And the uncontrolled variables really should be your dependent variable, or at least one of them should be. If you're using humans, there's going to be a lot of things you can't control. But the thing that you are not controlling is your dependent variable. And all of the things that you are controlling, you're attempting to leave your independent variable so that you get out an answer related to your dependent variable. So this independent variable is your x-axis, and it is your input. And then you get out your dependent variable, which goes on your y-axis, and it's considered your output, or the value that you're measuring. And then lastly, just remember to look at your graph. If it is not a scatter plot, think about how you could change your question. So if you change your question to a how question, how does something affect something else? Then this guy becomes your x-axis, your independent variable, and this guy becomes your y-axis, your dependent variable. Good luck.